now let's get on to the third demo in the series, right? So far what we saw was a bare metal program coming up on a Renode platform. Then we saw a slightly more complicated vExpress platform, right, the ARM Versatile Express platform, and saw that it's able to boot a version of Linux, but it was an old kernel. There wasn't really anything much that we could see over there. So does that mean that our Renode is sort of functionally limited in some way? Well, no. What we are going to do is next I'm going to run a script for booting on what's called the ZedBoard platform. Now the ZedBoard, some of you may have heard of, is basically very similar to the pink Z1 board that we use in the labs over here. What it does is that it has a full-blown ARM processor inside the FPGA, but Renode is only emulating the ARM processor part itself, right? And the interesting thing is the normal ZedBoard comes with images of Linux that can boot from SD card and can actually be used in order to directly log into the system itself, right? What we are going to do is to actually eventually compile our own kernel, but for the time being, the first demo that we will see will involve, okay, what does a ZedBoard platform look like and how do I basically boot something onto it, right? So let's quickly go through this. This is not something to be spending a whole lot of time on. There is one term that comes up over here called the device tree blob, which I'll be talking about more in later weeks, not so much in this. Right now we'll just sort of mention it and move on. So as far as the ZedBoard script is concerned, what we can see is, once again we have the using system bus, create a machine, load the ZedBoard platform description, show the UART analyzer, once again do a redirect, load the binary, which is the the actual Linux kernel image, the root file system, and one more file called the DTB, right, the device tree blob, which as I mentioned, we'll be talking about in more detail later. There is also some timer frequencies that can be set, right, but once again we have a very similar kind of macro defined over here, which basically allows us to load the bin file into the appropriate memory locations, set up the device table, right, which also has the different the console command line and so on, load the root file system into a particular memory location, right, and as you can see over here, the initrd memory location given here is where I load the root file system as well, and finally execute, right. Now one of the things that you need to keep in mind as I go through this is, when I talk about the speed of emulation over here, clearly this is far slower than actually running it on a board, right. But on the other hand, it's orders of magnitude faster than if you were trying to do a full Verilog level simulation of a CPU based system, right. So that is essentially what I mean by speed. It is that it is fast enough for us to actually see something like Linux booting up in real time, but at the same time is much slower than what would happen if I were actually running it on the board, okay. So this is what the script for the ZedBoard looks like. We'll also very quickly just look at the platform description. And the platform description primarily consists of the Zynq 7000 platform, right. And as you can see over here, somewhat similar to what was there in the Versatile Express platform, except that it basically says there are some network cards. This cadence gem is essentially saying that this is kind of a model that is provided by the company Cadence. It's not necessarily that it's anything else to do with Cadence, it's just that the model comes from them. Similarly, the UART also exists. There are I2C buses, SPI buses, the SD card, right, the memory map for the main memory, which as you can see actually starts from location number 0 itself in this case. There is another amount of on-chip memory which is quite small in size, as you can see over here. This is the so-called actual on-chip memory of the Zynq processor. 2 timers that are present in the system, right, and various other things until we finally get to our actual CPU, which is once again the same ARM v7A. Okay, so as you can see, very similar at a high level to what was there in the case of the Versatile Express, except that this now actually models something that is very close to a board that we have in our system, right. So what happens if I run Renode with the ZedBoard script? right? What it is going to do is to download the VM Linux file, which is the actual ELF file containing the kernel, a root file system, and the DTB file, all three of them. In this case, because I have run this once before to test things out, it has already cached the data somewhere locally, which means that it should be fairly fast. Otherwise, you will see that it actually takes time to download from the internet, and at that point you will see these messages coming down here in the logs telling you how far it has progressed in terms of downloading and so on. Okay. So what happens if I go ahead and run this ZedBoard script? As you can see over here, once again there is a show analyzer for UART0, as a result of which this message, or rather this window, pops up over here, right? And it tells you various things such as, you know, loading the data, fixing the PC address, and then finally loading the 16 megabytes of init RAM disk into this particular location as specified in the script. Now what happens when I try running this? Let's go ahead, in fact let's first take a look at what is at different locations, and if I do this, interestingly enough, this one actually has memory registered at this particular location, right? And you can go look at the different values that are there in the REPL, the platform, and check whether all of them show up properly in terms of the bus. But what I'm going to do now is to basically get started, right? Let's go ahead with booting, and as you can see very quickly I started seeing messages out here, right? And it has now come to the point where it actually says yes, an ext2 file system was found in the RAM disk. It is taking that 16 megabytes and loading it into the RAM disk, right? All of this is because the kernel knows how to take binary data, load it into a RAM disk, and then treat that as a set of files that it can execute, right? And yes, we have gone all the way through over here. It is actually booted up with an essentially complete Linux based system. This is where you start to see that the system can actually be a little slow, because a normal system would most likely have already finished booting by now, right? Whereas over here it still took us some time, right? Finally it comes to this login, where in this case it's not really asking for a password. I can just enter root and it gives me this location. Now this is a full Linux system, right? Some of these messages keep popping up in between. That's because these are essentially the console messages that are going to keep coming over there. I'm going to just ignore them for now, right? I can, for example, look at the present working directory and it's /root, right? So better than the previous case where it basically sort of crashed into the home, the / folder, and didn't actually even go into the proper location, right? If I look at the CPU info, it tells me that this is basically the Xilinx Zynq platform, which in this case has an ARM v7 processor and so on, okay? In this case I can actually look for something more. I can look for whether modules have been loaded, right? And it turns out there are no modules loaded by default over here. But what's interesting is we will now build on top of this, and we'll see that later on we can actually go ahead and build our own module if we want to, right? The command uname is also useful, right? It basically tells us that now this is a much more recent Linux kernel. It's 6.1 something, right? Compiled in 2023. It's still targeting the ARM v7L platform, right? So all of this is useful information for us from the point of view of how to boot Linux, okay? So what we have seen now is the ZedBoard is a more complicated version of a platform, which is, as we can see in this case, booting a fairly recent version of Linux, right? And we can actually get it to the point where this is usable, right? I can actually sort of use it and emulate the, pretend like I'm working on a real Linux system by typing in commands directly over here. This is literally how it would be if you were to log in on the serial console corresponding to a ZedBoard, okay? Now what we would like to do is that I actually want to be able to compile a module corresponding to my registers and load them into the, load it as a module into the system, and from that point onwards to actually sort of make it, at least to start off by pretending that there's a actual physical device present over there and see how it behaves, right? Now the modeling of the physical device and so on is more complicated, so we'll get to that later. But what is useful for us now is to take one step back and say, okay, if I just wanted to compile a module and load it in here, how would I do that? Unfortunately, it turns out that's more complicated than it seems at first sight, because the modules that get loaded into the Linux kernel have to be compiled against the same build information essentially that was used in order to build this particular kernel, right? What does that mean? Building just means compiling. So in other words, there's a particular version of GCC that I need to use, right, which can be used in order to generate an output corresponding to this particular kernel. So it looks reasonable that I should be able to maybe get the kernel source code and if possible just go ahead and compile it and get things working. Turns out it is not as simple as that. The primary reason being that we don't have access to the built version of the kernel. We only have the final kernel that has been downloaded directly from the Antmicro website. So rather than trying to sort of recreate and find out how exactly they had compiled it, it turns out that it is easier for us to just compile a fresh kernel of our own, load it into the system and see how things go. Okay.